So here in chapter 8, we're going to talk about chemical composition. We're going to talk about some important calculations like calculating grams, moles. We'll also talk about some types of formulas, empirical and molecular formulas as well. So let's get going here on it. So first, we're going to talk about atomic masses a little bit. And the atomic mass is, as we might have touched upon earlier, for example, those numbers that you see on the bottom of the periodic table there are the atomic masses. Um, they are the fundamental properties of a mass, which is obviously based on the number of protons, electrons, and neutrons that are present. Unfortunately, right, they are super small, so you can't like pick one up and put it on a scale or anything like that to figure out the mass of it. So typically speaking, when we don't have a way to sort of directly measure something, a lot of times in chemistry, they will pick something to use as sort of a standard to sort of compare everybody. So in the case of atomic masses, they chose an isotope of carbon, which is the carbon-12 isotope, as really the standard isotope to compare everybody else's sort of mass to. Now, the carbon-12 isotope is a guy that has basically 6 protons and 6 neutrons, and it has a mass of a 12 was referred to as AMU. So the carbon-12 isotope, which is sort of the standard, has a mass of 12 AMU, which stands for atomic mass unit. Atomic mass unit is a unit, obviously, of mass. I will be honest with you, you probably don't use it all that much outside of maybe this chapter, a little bit. We don't usually use it, but that is also the unit that we can use from the periodic table when we look at the atomic mass. So for example, if we looked at hydrogen, we could say that for hydrogen, there is 1.008 AMU per atom of hydrogen. And we typically do take it for any use. We usually take it to about 4 significant figures when we pull it off the periodic table. And we will use it more commonly a little bit later on in this chapter. We will use it as the molar mass, which numerically they're going to be actually the same number, but that's more useful way that we use these numbers, which tells us basically how many grams per mole, as grams is a more useful unit for us than say AMU. So the atomic mass unit is a mass that's equal to basically 1/12 the mass of a carbon-12 atom. And AMU is also called the Dalton. Nobody even mentions that not too much anymore, as you don't usually see that unit all used very much, Dalton. So the atomic mass unit, which is the atomic weight, is basically, again, the mass of these elements that we find. So for example, experiments have shown that hydrogen on average is only about 8.4 as big as the carbon-12 isotope. So frankly, they do a little calculation, say like this. That's 8.4% converted into a decimal, right? Divide by 100 or move the decimal place 2 places to the left. And we get something like, again, 1.008. Same thing if we look on the periodic table, we will see the atomic masses of everybody up there, you know, like iron is 5585, which means iron has 5585 AMU per atom, as again a way to use the atomic mass that you find from the periodic table. The atomic mass, and later, as we'll talk about really here in this chapter, and more so how we use these numbers, which is the molar mass, they're really used as conversion factors. So they're kind of used as conversion factors to sort of change units. And again, probably not a ton of AMU usage throughout most of your calculations in chemistry, as we will see it. So if they use carbon as sort of the standard isotope to compare everybody to, when you look at the periodic table, though, you actually do not see 12.00 for the atomic mass of carbon. You do see 12.01, which you might think, well, if that is the standard, shouldn't it have a mass of what we actually see there with carbon-12? And the answer is what we actually do see on the periodic table for all the numbers that are underneath the symbols, they're actually the average atomic masses, although most people don't call it average atomic masses, but they're basically the average atomic masses of all the naturally occurring isotopes for that particular element. Remember, isotopes, right, are the same element, but they have different numbers of neutrons, right, which they have a different mass number and they have different masses. So for example, something like carbon, there's a carbon-12 isotope, there's a carbon-13 isotope, and when you sort of do the average calculation, you get something like 12.01, which is sort of what we see there. So really all the numbers that we see on the bottom there, also a good reminder again, those are not the mass numbers, right? So these are the atomic masses. They are of the naturally occurring isotopes for those particular elements. And again, we could do a calculation to basically figure out the average atomic mass. And the way that we do the calculation is through this sort of formula. If we wanted to calculate the atomic mass that we see there on the periodic table, we take the percent abundance of the first isotope and we times it by the atomic mass of the first isotope. And then we actually add it, and people always want to multiply here, but we do add it here, and we take the percent abundance of the next isotope, the second isotope, times the atomic mass of the second isotope. And then we really just kind of continue that pattern, however many naturally occurring isotopes that we have. The percent abundance is also sometimes called the relative abundance or percent relative abundance. That's basically the percentage of how often those naturally occurring isotopes sort of occur in nature. Obviously, in order to get all of the naturally occurring isotopes, your percentages should add up to 100, right? So if you come across a problem where your percentages really do not add up to 100, you're probably missing something in terms of a naturally occurring isotope. How do they figure out sort of relative abundance, the masses of these different isotopes? They do something that we're not going to go too much into detail, but they do something that's known, for example, as mass spec. And they basically send a sample down, they heat it up. It's got like a magnetic field and electrical field sort of. And what happens is it will sort of separate out each of the isotopes as it sort of spun down this mass spec. It'll come out on the sort of diagram that comes out as a result of it as different peaks. And those peaks are used to figure out the percentage of each of those different isotopes. The different peaks are separated out by mass, so they separate out by size as it kind of goes through there, and they're able to determine the naturally occurring isotopes and really the relative abundance or percent abundance of each of those sort of occurring. And that's sort of what's sometimes referred to as mass spec. So for example, if we take something here like carbon, as I mentioned before, what we see is the carbon-12 isotope and the carbon-13 isotope are basically the two common isotopes that we see for carbon. And the carbon-12 isotope occurs about 99% of the time, while the carbon-13 isotope occurs about 1% of the time. The carbon-13 isotope has a mass of 13.00335 AMU. And the carbon-12 isotope, as we talked about, bless you, has a mass of 12 exactly. So if we do our formula here that we just talked about, this is the percent abundance of the first one, again, converting that percentage into a decimal. And that is the atomic mass of our first isotope. This is the percentage of the second guy converted into a decimal times the atomic mass of our second isotope. Once again, as I mentioned before, you do want to make sure that, again, these guys do add up to about 100. It may not be perfectly at 100, but should be pretty close to that 100 ballpark. Otherwise, again, you are missing something. So once again, it is a addition here, not a multiplication. And we are going to get something like 12.01, which is what we see there on the periodic table underneath carbon. Now, it's important to remember that you would never really find a carbon atom that has a mass of 12.01, you would either find a carbon atom that's really the carbon 12 isotope that has a mass of 12, or the carbon 13 isotope that has a mass of 13 and change. But again, what we use there on the periodic table is the average atomic masses of each of those guys. Any questions on that there? So why don't you try this one here? Might be a little different than what you have on your handout. So why don't you give this one a go? Bromine 79 is 50.70 and has a mass of 79.92. Bromine 81 is 49.32, has a mass of 80.92. What is the atomic mass of bromine? Okay, so let's take a look. So once again, we have a couple different isotopes here of bromine. We are given the percentages of each of these, and we just quickly look at it at about 50 and 50, which is about 100%. So again, we're not missing any type of isotope. By the way, if they didn't give us one of the percentages right, we could figure out the other by subtracting from 100, right? Because that should give us all of the naturally occurring isotopes. So if you need to figure out the percentage that's missing, you could do that by subtracting. So we're going to take basically our atomic mass is going to equal our percentage of the first one, which again, could either divide by 100 or move the decimal point 2 places to the left. So that's what I'm going to do there. We're going to times it by 7992 AMU. We're then going to add it to our second isotope, which once again, you could either move the decimal place if you want or divide by 100, which will move it for you, whichever way you want to do it. And if we do all that good stuff there, that's going to be 0.507 times 7992 plus and in this case here, let's fix my calculator and try it one more time here. There we go. All right, so 0.5070 times. All right, so we ended up with 8043 in this case here. 8043 AMU. Yeah. Any questions on that there? All right, so let's take a look at I think the one you have on your handout there. Let's see here what it says. I apparently lost it somewhere. So we have an isotope that is 70.5% abundant with an atomic mass of 117.80 AMU. While the abundance of the other one is 29.5% with an atomic mass of 120.8. All right, so I'm going to take a sec there and calculate this one here, see what you come up with. Okay, so once again here, just gonna kind of look, we got 70-ish, 30-ish, so again, that's 100, so we're not missing any percentages. So we're going to take our first isotope there, convert it there into a decimal, the percentage, times it by the atomic mass there of our first isotope, plus our second guy here, times our 120.85 AMU. And if we do all that good stuff there, looks like 118.7 AMU. And if we take a look at the periodic table, that is probably our friend 10, right? Is probably who that would be in this particular case. Yes. Any questions on that or how to calculate the average atomic mass? So once again, that is how we calculate and sort of get those numbers that we see there of all the naturally occurring isotopes for this particular element. And once again, you can use it as a conversion factor, something like this. Or again, flip it around and use it like this. All right, so let's talk a little bit more about some of these relationships here. Atoms have very tiny masses, so they created a unit to avoid these very small numbers, and that again is the AMU. For relationship purposes there, an atomic mass unit is equal to about 1.66 times 10 to the minus 24 grams. So very, very small number in terms of grams. So we do use atomic mass units, but really not all that much. As I mentioned earlier, grams per mole, and grams is more of a useful sort of units that we use a lot in chemistry. So we just talked about that there. So if we were to use these atomic masses from the periodic table to do some conversions, if we want to calculate the mass in AMU of 431 atoms of carbon, we would again go to carbon. We would find our number on the bottom. And once again, it is typical to go with 4 significant figures when you pull it off there. And again, that will give us our 2 conversion factors, 12.01 AMU over an atom, or you could flip it around, an atom over 12.01 AMU. Taking a dimensional analysis approach, we will start with our atoms. So remember, we want to go opposites to get them to cancel. So our guy on the left here will do that. Atoms will cancel. We'll end up with 5176 AMU, which would be, again, the mass of those 431 atoms of carbon. Same thing here with our aluminum. We go to aluminum and look on the periodic table there, we'll see 2698 on the bottom, and that's going to give us our 2 conversion factors of 2698 AMU per atom. An atom is 2698 AMU. Once again, we're going to start with our 75 atoms. We're going to go opposites so that they cancel, and again gives us a mass in AMU, which not so helpful a lot of times if you can't go into the lab and weigh out, like I want 24 AMU. Again, not such a useful practical unit these days, but again, you do need to still know how to do these conversions here. Any questions on that there? All right, so let's then talk really about more useful sort of conversions. And these are molar mass and our friend Avogadro and his number. Uh, First off, molar mass has units of grams per mole, which, as we will see, is a much better unit than our AMU, each sort of unit. Avogadro's number is used in certain situations, but these are really 2 conversion factors is really how you should think of them. There are really 2 conversion factors that allow us to change between different units. The molar mass, as we will talk about, is our conversion factor to go from grams to moles, which is a unit we'll talk about in just a second, or backwards really from moles back to grams. So that's really the conversion factor that we use to kind of go either way, depending on whichever way you will need to go. Avogadro's number, as we will talk about, is typically a conversion factor that we use to go from moles to atoms, or maybe molecules as well, or backwards from atoms or molecules back to moles. So that's Avogadro's number. So as we kind of go through this, you just really think of these as sort of conversion factors. And there's just 2 different places that we get these conversion factors, rather than maybe just looking it up in a table or something like that as to how we get these 2 values. So we're going to start with Avogadro's number, I think, first here. And the idea of the mole, so not the furry little guy, but this is the mole here in chemistry. So in life, we have a lot of words that represent a certain value of something. We have pair, which means you have 2 of something. If we have a dozen, it means you got 12. A gross of pencils, for example, you have 144, in case you've never heard of that. So in chemistry, we do have sort of a word that represents a certain amount of something, and that is the mole. And this abbreviation here of MOL is the abbreviation for mole. They had to cut something off, so they cut the E off there to abbreviate it. The reason it's really important to remember that that is the abbreviation for mole is a lot of times when people see that in problems or they're doing some type of calculation, a lot of times people's minds go automatically to molecules when they see that. So again, it's not an abbreviation for molecules. It is the abbreviation for moles, and you want to make sure that you keep that. So what is a mole? A mole is really the amount of substances that contain either atoms or molecules that there are in exactly 12 grams of our carbon-12 isotope. So 1 mole of anything will equal this number here, 6.022 times 10 to the 23. And as we'll talk about in a second, that is our friend Avogadro's number, Avogadro number, whatever it is there, Avogadro's number. Now, what also confuses people is the units that go with that number could really be anything that you want. So a lot of times here we use atoms. You could use molecules. You could use particles. You could use pizzas, shoes, whatever it may be. Although the occasional pizza and shoe comes into a question, most of the time probably is going to be atoms and molecules are the 2 units that we will see the most with it. So technically speaking, again, the units that go with it can really be anything. Just like, if you had a dozen donuts, right? Or you had a dozen roses, right? Their dozen basically means 12 for both of them. So you got 12 donuts, 12 roses. So the units will change, but the number basically means the same thing as we do here. So if you have a mole of anything, that is how many atoms or molecules, for example, that you do have. Questions on that there. So that is Avogadro's number, experimentally found to be that, but that is the number clearly that they want to know. So 6.022 times 10 to the 23 is Avogadro's number. Once again, will not be given to you, and you are expected to know it. We basically use Avogadro's number, as I mentioned earlier, as a conversion factor to go between the units of moles and atoms or molecules or back. And we use it as a conversion factor, and you can do it for anything. So for example, if I had 1 mole of hydrogen, I would have how many hydrogen atoms? It would be 6.022 times 10 to the 23 atoms of hydrogen. This will give me 2 conversion factors that I could use in a problem, which is 1 mole of hydrogen over 6.022 times 10 to the 23 atoms. Or you could flip it around, 6.022 times 10 to the 23 atoms over 1 mole of hydrogen. If I had 1 mole of iron, it would also be 6.022 times 10 to the 23 atoms of iron, which again, you could write the 2 conversion factors. If I had 1 mole of water, how many molecules would I have? I would still have 6.022 times 10 to the 23 molecules here. So 6.022 times 10 to the 23 molecules of water. Here we use molecules because water is a molecule. If it's just an element by itself, we use atoms as sort of the unit involved there. We could write the same sort of conversion factors, 1 mole of water over 6.022 times 10 to the 23 molecules, or 6.022 times 10 to the 23 molecules over 1 mole of water. Now, will you use each of these conversion factors in a problem? The answer is no, otherwise you're undoing your calculation. So just like a normal sort of dimensional analysis conversion factor type problem, you're just going to pick whichever one you need, which is the opposite location to cancel out the units, which is what you're looking for. Now, sometimes people go crazy with Avogadro's number because they're like, they make me know this number. I have to know this number. I should just use it in every calculation ever known to man. And you should not do that. You should only use Avogadro's number if you are given a number in atoms, molecules, particles, or something like that. or you're asked to solve for something in atoms, molecules, or particles. If there's really no mention of like atoms and molecules, those are like the key two words usually, you should leave Avogadro's number on the side. So sometimes people will incorporate it into the calculation where it's not needed. And those are kind of the words that you want to look for. Any questions on that there? Clearly as well, you want to make sure you're using your exponent button right on your calculator when you punch that in. So the term mole, as I mentioned before, and Avogadro's number, again, refers to anything. And you can't take anything off the periodic table and you go, if I have 1 mole lithium, I would have 6.022 times 10 to 23 atoms of lithium. Anything that is a molecule, if I had 1 mole of methane, CH4, I would have 6.022 times 10 to 23 molecules of methane. Now, probably the conversion factor really that we will use the most, or that you'll use the most as you go through chemistry, which is a really important one, and that is molar mass. And molar mass has 2 units, which are grams per mole. And the number always stays with the grams part, and it's always per 1 mole. The molar mass is the amount of grams or kilograms in 1 mole of a substance. It is based off of our carbon-12 isotopes. And it also is found, surprisingly enough, in the exact same spot on the periodic table as the atomic mass, because numerically speaking, the atomic mass in AMU per atom and grams per mole are the same number. So they're exact same number. And most of the time, we don't really use AMU per atom. We will use it as grams per mole, which is the molar mass. So for example, here, I could say in 1 mole of carbon, there are 12.01 grams of carbon, which will give me the molar mass of carbon here of 12.01 grams per mole. And again, you could think of it as a conversion factor. You could say that there are 12.01 grams of carbon per mole, or you could flip it around, mole of carbon, 12.01 grams. So we use it as a conversion factor. And as I mentioned before, it is your conversion factor to go from grams to moles and moles back to grams. And that is a calculation we do a lot in chemistry doing this. You could do something like water that we had previously. You would go to the periodic table and look up hydrogen. You would go to the periodic table, look up oxygen. And again, we take it to 4 significant figures. And if we wanted to calculate the molar mass of this guy, we just add up the parts. So there's 2 hydrogens, each at 1.008 grams per mole. There's 1 oxygen at 16 grams per mole, which means the molar mass of water is 18.02 there, or 1. O2 grams per mole. That again gives us 2 conversion factors of 18.02 grams per mole of water, or a mole of water is 18.02 grams. So you want to think of molar mass as really a conversion factor. To do so, you go to the periodic table to get it, and again, it's the number on the bottom. Now, a couple things about molar mass, which may not make a whole bunch of sense at this point, but hopefully it will. And we'll talk a little bit about it when we get kind of there later on, is sometimes, let's just say you had a chemical equation or something like that, and you had, I don't know, say 2 waters in the chemical equation, and you were going to do a calculation, for example, where you needed the molar mass. When you calculate the molar mass, regardless if there happens to be a number in front of it, say in an equation or anything like that, you should never calculate the molar mass based on any other number other than just the actual formula. So if you just take the formula by itself, that is always how you should calculate the molar mass. So sometimes later on when we use this, when we're using equations as well, people kind of incorporate the number they see in the equation in the molar mass. And you shouldn't do that, because that's basically what the definition of molar mass is how many grams there are in 1 mole of that particular guy. And 1 mole basically means you just take the formula by itself and add up all the parts that are in one formula by itself to get the molar mass. Any questions on that there? Once again, this not use both of those conversion factors, whichever one will get you there. And this is a very, very common conversion that's used. So for example, if I had 1 mole of carbon, that would be 12.01 grams of carbon, right? And that would also be the way it ties into Avogadro's number, 6.022 times 10 to the 23 atoms of carbon. So that is how they are all sort of related to each other. Once again, if I had 1 mole of water, that would equal 18.02 grams of water. And that 1 mole of water would equal 6.022 times 10 to the 23 molecules of water. So for example, here, if we had, what is the molar mass of CH4? And why don't we do CO2? And why don't we do sulfur? So I can give you some things from the periodic table. It'll be helpful. Carbon, hydrogen, oxygen, and sulfur here. Okay, let's take a look. So once again, if you were asked to calculate the molar mass or just need to calculate the molar mass, which is more often how you probably use it, is you just kind of need it as a conversion factor. So you got to go calculate it. Always to the periodic table, and always, again, the numbers on the bottom to 4 significant figures. So in the case of CH4, we're going to add up, again, all the parts. So we got 1 carbon at 1201. We got 4 hydrogens, each at 1.008. And that will give us a molar mass here for our methane in this case of 1604. Once again, the units are grams per mole, and the number again always stays with the grams part and is 1 mole. And again, we could use it as a conversion factor as 1604 grams over 1 mole, or 1 mole on top over 16.04 grams. Question on that one there. Coming to CO2, same thing. We're just going to add up the parts here. So we got our carbon. And in this case, we got a couple of oxygens, each at 16. It's like a 4401 grams per mole. Once again, number stays with the grams part per 1 mole. So again, that 4401 grams on top over 1 mole, or flip it, 1 mole over 44.01 grams. Here for sulfur, pretty much that's the only thing there. So we just take it straight from the periodic table, and it would mean that there are 32.07 grams per mole as the molar mass there of sulfur. And once again, we could use that as a conversion factor as well. Any questions on any of those there? So again, as I mentioned, most of the time, you're not going to have probably a question that's straight up to ask you to calculate the molar mass. You're just going to need to do it as part of a calculation that you're doing. So just keep in mind that you always sort of have that available to you to use as a conversion factor. And once again, these are the conversion factors from grams to moles, and backwards is where we use that molar. All right. We already see this, I think. I scribbled on it. It's all right. We kind of talked about that relationship earlier. All right. So a reminder that Avogadro's number and really molar mass can be used to do those conversions. And once again, as I said earlier, do not use Avogadro's number in places where you do not need to use it. The keywords to think about are atoms or molecules being involved in the question. And again, if there are no atoms or molecules involved, then definitely should leave Avogadro's number on the side. And again, these are just the two ways that we can use Avogadro's number and molar mass. All right, so let's do some examples here. How many moles of helium are there in 5.46 moles of helium? Give you this here. Helium is 4.003. All right, take a moment, set it up. The calculus is no. We have moles, which again are not molecules, and we have grams. So no mention of atoms, no mention of molecules or anything like that. So you do not need to use Avogadro's number. This is basically a grams to moles situation, which is our molar mass that we get from the periodic table here. So once again, this means that there are 4.003 grams per mole of helium. And again, we could use it as really two types of conversion factors, such as this. And here we're going to start with what was given to us. So 5.46 grams of helium. Remember, when we do dimensional analysis, opposites cancel, which means we are going to roll with this conversion factor here. That should leave us moles when it's all said and done on moles of helium. 4.003 grams. Once again, the grams will cancel, and that will get us 5.46 divided by 4.003, about 1.36 here. Moles of helium. Significant figure-wise would not look there, would look at the original number in terms of significant figures, which has 3, and we would end up with 3 in this case. Any questions on that one there? That is a very, very common conversion that you do a lot, taking from grams to moles. And a lot of calculations that we do, that's like the first step that you do is take the grams they give you and convert them to moles using the molar mass. Any questions on that one? All right, so why don't you try this one? What is the mass of one gold atom? The molar mass of gold, if we look on the periodic table there, is 197. What is the mass of just one single gold atom? So I'll just kind of scratch all that out. We'll just do this question right there. Okay, so let's take a look at this. Do we need to use Avogadro's number here? The answer is yes, because we do have atoms, right? And we're going to need to go from really atoms to moles and then moles to grams. A reminder that Avogadro's number is what we use to go from atoms back to moles. And then once we have it in moles, we could use the molar mass to take it kind of the rest of the way there. So in this case, we will start with Avogadro's number. And that means, again, in 1 mole of gold, there would be 6.022 times 10 to the 23. These would be atoms since we're just talking about gold. Present. So we'll start with our 1 gold atom. Once again, we want to go opposite to get the atoms to cancel. So we will need to put Avogadro's number there on the bottom. And if I stop the calculation right at this point, I am going to be in moles of gold, which gets me to here. At this point, I then need to take it the rest of the way, which is going to be our molar mass from the periodic table, which is right there. And that would mean that the molar mass, once again, here of gold is 197 grams per mole, which we could use as a conversion factor. You could get an answer, or you could just continue on with the calculation here. We see moles on top, which means moles has to go on the bottom using our molar mass value here. So once again, molar mass here, Avogadro's number here. And the moles are going to cancel, and that's going to leave us grams. We're going to multiply across the top, which is basically 197 divided by Avogadro's number, making sure to use our exponent button. And we are going. That is a large number, small number. As it went off of the molar mass in this case, because one atom, for example, would be maybe like an exact number, like you're counting. So you could really use any number of significant figures for your answer in this case. Any question on that calculation here? All right, so let's try a few more here. Just make sure. Let's go with how many grams of zinc are there in 0.256 moles of zinc? Zinc on the periodic table has changed, no longer 6539. So I guess we'll go with what it says nowadays, 6538. Pretty close. Not need to use Avogadro's number. A reminder that the MOL here is moles and not molecules. So we are just going from moles to grams. And once again, that is the molar mass from the periodic table that's going to allow us to do that. We will pull the number here off the periodic table, which tells us for zinc is 6538 grams per mole. It's a molar mass of zinc. And we will use that as a conversion factor. So 0.256 moles of zinc. Once again, we need the moles to cancel. So that's going to go on the bottom. And again, the number always stays with the grams part. So that goes up on top. Our moles here. And that's going to give us 0.256 times 6538. We'll go with 16.7 in this case. Grams of zinc. Once again, sig figs based off of the first number here. There's an exact number in this calculation. Any question on that one there? I would highly recommend that you again set it up like you're using dimensional analysis so you can see the units in the right locations. And again, it'll help you with multiplying or dividing when you should do those things. Let's take a look at a few more here. For each of these, calculate how many moles there are of ethanol and how many molecules there are of the same amount of ethanol. I'm going to give you some numbers again. Carbon 12.01, hydrogen 1.008, and the okay, so let's take a look. So the first one here is how many moles are there in 23.2 grams. So again, this is a grams to mole conversion, which means we do not need Avogadro's number for this first part. It is just the molar mass from the periodic table. We do need to add up the molar mass here of our ethanol. So we do have 2 carbons, each at 12.01, basically for our carbons. We also have 6 hydrogens, each at 1.008, basically our hydrogens, and our 1 oxygen at 16 in this case. That's going to give us 4607, I believe, grams per mole as our molar mass here from the periodic table. Any questions on that there? So again, here, nothing mentioned about molar mass in this problem, just has to go to the table to kind of use as a conversion factor. So we'll do it here at 23.2 grams of ethanol. We're going to go opposite here to get rid of grams. So we're going to put the grams on the bottom, which will have the number associated with it. Grams are going to cancel, and that's going to get us 23.2 divided by, there you go, 46.07. We can go with 0.504, it looks like maybe. Any questions on that one there? Now, at this point, we're looking for molecules of the same amount. So that keyword there is molecules means that is Avogadro's number, basically what we need to use. And again, we're going to go in this case from moles to molecules. And Avogadro's number is going to allow us to do that. So we can actually just pick up with our number there that we had above, since it's the same starting part. Obviously, if it was one problem, you would just kind of continue the calculation that way. In this case, we know that 1 mole of ethanol is equal to 6.022 times 10 to the 23 molecules of ethanol. Here again, we do use molecules because we're talking about a molecule rather than just an element by itself. In this case, we want moles on the bottom. So 1 mole here will go on the bottom. Avogadro's number will go up on top. And if we do that there, 6.022 to the 23. Looks like 3.03 to 23. Any questions on either of those calculations there? And again, if it was just the question of how many molecules there were in 23.2 grams of ethanol, you basically just combo both steps together, obviously, to get to the end there. Let's try one more here to finish it out, maybe for today. What is the mass in grams of 1 molecule caffeine? So again, our numbers here: carbon, hydrogen, nitrogen, and oxygen. All right, so how many mass in grams of 1 molecule of caffeine here? Okay, so let's take a look. Once again, here we're looking for those keywords. So I do see molecule, which makes me think I need to use Avogadro's numbers somewhere along the way. And in this case, we're actually starting with molecules. So we are going to take this pathway of molecules to moles to grams. Remember, moles are sort of the center guy that ties both of those units together. And again, it's going to be Avogadro's number to get us to moles. And at that point, our molar mass there to take us to grams. So we do need to calculate the molar mass. So to get the molar mass of this guy, there are 8 carbons at 12.01. There are 10 hydrogens at 1.008. There are 4 nitrogens at 1401. And again, all these come from the periodic table. We're grabbing these numbers, and 16 grams per mole. All of them basically come from the periodic table there. And if we do all that good stuff there, we end up with 194.2 grams per mole. So again, we're going to use that eventually here in our calculation as a conversion factor. We're going to start with our 1 molecule. And just like previously here, we know that 1 mole of our caffeine will give us 6.022 times 10 to the 23 molecules. And that's our Avogadro's number. So opposites to cancel, molecules on the bottom. So that's going to put the Avogadro's number on the bottom here. And 1 mole of our caffeine here. If I stop the calculation right at this point, my molecules cancel. And now I need to take it from moles to grams using my molar mass. So I can see that my moles are up on top. So I do want my moles from my molar mass on the bottom. The moles here will cancel. We're going to basically take 194.2 and divide it by 6.022 to the 23. And we'll end up with something like 3.225 times 10 to the minus 22 grams of our caffeine in this case. Question on that calculation. Once again, Avogadro's number, molar mass from the periodic table. Any questions on that? Definitely grams of moles of grams. Need to know how to do that perfectly because it is in a lot of calculations as we continue our journey here. Yeah. All right, we'll lay it up there for today.